welcome to another online learning day. Today, what we're going to be talking about, the essential question is, what is the chemistry of phase changes? So this means like melting or boiling or that kind of idea. That's what I mean by phase change. What's the chemistry behind that? So related to kinetic molecular theory and what we know about particles and energy, we're going to be able to explain why do things melt or freeze or boil. Before we do that though, let's do a little bell ringer warm-up question related to our last note. So why is it unlikely that Lake Superior, that huge lake up in northern Minnesota, why is it unlikely that that lake ever completely freezes in the winter, nor does it usually get very warm in the summer? Use some time right now, go and pause the video, think about what your answer would be. Pretend this was a quiz question, a short answer. What would you say? All right, come on back. Did you get an answer? So you might have said something like, well, it's huge, right? It's a huge lake, so it takes a lot of energy before that lake water either would freeze or would get really warm. So it's specific heat capacity, right? There's a huge amount of mass, so it would need to absorb and change a lot of joules of energy before it would actually change its temperature. So to get cold enough, changing its temperature to freeze, or to get warm enough to change its temperature to be warm in the summer, it's because it's a huge amount of mass and the specific heat capacity for water is really high. So maybe that's something you've experienced before and wondered compared to other lakes around here. That's one of the reasons why Lake Superior does what it does, the superior lake that it is. All right, so that's just a little kind of warm-up question to get you thinking about the stuff we talked about on our last time together. Now, let's go ahead and get into today's topic. So would you please set up your focused note page? The topic is phase changes. Write down whatever date it is that you're taking these notes. And the essential question again is, what is the chemistry that explains phase changes? So the focus today again is, what do we know about chemistry and particles and energy that would explain why something starts to boil or freeze or melt or any of those kinds of phase changes. All right, pause the video if you need more time setting up your notes. Otherwise, let's get into it. I want to show you is this phase change triangle. It's got our three main states of matter, and then it's got back and forth arrows between them. What I'd like you to do is, just based on what you already know, I'm going to have you pause the video. There it is again. Pause the video and label these 7 different things. Now, yes, there's only 6 arrows, so that means that one arrow is going to have 2 words on it. So based on what you already know, see if you can fill those in. So melting, freezing, evaporation, boiling, condensation, sublimation, deposition. So every arrow will have one of these words, and one arrow will have 2 of them. Pause the video. From what you know, label the diagram with these terms. Go ahead. All right, welcome back. Let's see if we agree with each other about where those words would go. So let's talk about between solids and liquids and solids first. So if I go from a solid to a liquid, that's called melting. If I go the opposite, that's called freezing. So this has to do with adding energy and removing energy. Here, the solid particles get enough energy that they break apart from their attractions, they move fast enough, and they start rolling over each other. Now they're liquid. Here, I freeze, so I remove energy, and then those liquid particles now become more and more attracted to each other until eventually they are considered solids. The opposite, or not the opposite, the next round, liquid to gas, is evaporation. So I'm giving these particles enough energy that those liquid particles don't attract to each other. They have enough energy, they move and they spread out and they become gases. But that's also called boiling. So we'll talk about the difference of these in just a little bit, so you can be thinking about that. If I have a gas that goes back to a liquid, that's condensation. These gas particles have lost enough energy that they are now more attracted to each other. They can't spread out as much. They can't move as fast. So they become liquid. They roll over each other. Now, these solid to gas or gas to solids, we don't talk about that as much, but these are things that there are things in your world where you might have seen them. If I go from a solid to a gas, that is sublimation. And my best example of this is if you've ever seen dry ice. Dry ice is solid carbon dioxide. Well, we know that normally carbon dioxide is a gas. At just even room temperature or even pretty cold, you would have carbon dioxide gas. So if you are able to make solid carbon dioxide, you have cooled down those gas particles so unnaturally, like in terms of what they want to do, so that if you take that solid and put it at room temperature, those particles get so much energy so fast, they turn into a gas. They don't become liquid first. The opposite, gas to solid, is called deposition. And this also sounds weird, but we have a really easy example of this in our world here in Minnesota. This is what frost is. So you've got water vapor that's in the air at all times, even when it's really cold out. And when that water vapor in the air, even on a really cold, snowy winter morning, if it hits something solid like your windshield, though that water vapor in the air cools down so quickly that it doesn't turn into a liquid, it just turns into a solid. That's what frost is. So just to give you that kind of connection. All right. So these are hopefully words that make sense to you now, or they already did, and you can see the relationships between solids, liquids, and gases. So our focus today is going to be mostly on boiling, evaporation stuff, but we'll talk about all of them a little bit. All right, so I've got a thinking question for you. We put boiling and evaporation on the same arrow. They both mean to go from a liquid to a gas. But what is different about them? Go ahead and pause the video and think about that and write down your idea. All right. So the main difference is that evaporation happens at the surface level, and that's it. So just at the surface level, because it's collecting energy from the air around it, and that's what gives these particles the energy to turn into a gas and leave. Boiling, the gas particles happen anywhere. So usually you have a heat source. That's what we think of as boiling. If you put, a pot of water on the stove to make some noodles, you boil it first. And so you are adding heat. So that heat is spreading all the way through the sample, and any of those particles can collect enough energy, and then they overcome the atmospheric pressure, and then they turn into a gas. So that's our main difference between evaporation and boiling. Now, the other thinking question I want you to have for a little bit, so again, pause the video and then jot down your ideas. Why is evaporation a cooling process? How could it be cooling if those particles have high energy? Think about that. All right, let's talk about evaporation as a cooling process. So here's what's happening. Just these top layer particles are collecting energy from the air around it. They collect enough energy, and then where do they go? They leave. So all the particles behind have lower energy and they stay liquid. Eventually, the new top layer gets enough energy, and those particles turn into gas and they leave. So because they have the highest energy, and the ones left behind have lower energy, and that process would repeat itself until this whole sample was gone. Like maybe you've ever left a glass of juice or a glass of water like in your room for a few days and forgot about it, and then you went back and you're like, oh, all the liquid is gone. Well, this is what happened to it. So the highest energy particles are gone. The lower energy particles are still there. So the overall effect is that it is a lower energy, lower temperature, so it feels cooler. This is what happens with our bodies. So this is a good thing. So if you're working out a lot, or if you're somewhere where it's really, really hot, for your body to maintain a safe internal temperature, it releases some water. That's what sweating is. Because when you sweat, that liquid on the outside of your skin has a lot of energy because it's hot. So then that water will get enough energy and will evaporate. And it brings the high energy water particles with it and leaves. So then the leftover particles have lower energy, lower temperature. So then that cools you down. So that's a good thing. So then that helps lower the temperature of your body. So sweating is a good thing. The only time it's a bad thing is if you also are like dirty, or if you have bacteria on your skin, and that's when it smells bad. But just the actual process of sweat is actually really good. All right, go ahead and do a level 1 question about any of our stuff so far. Maybe you would redraw the empty phase change diagram and say, label this diagram. That would be level 1 because it comes right from the notes. So labeling that diagram. Yeah, that's probably a good level 1 question. All right, you come up with your own though. Excuse me. All right, let's keep going. The next thing I want to talk about is just phase changes in terms of energy, right? So here we have a picture of a solid, and then we have that it freezes, and then we have a picture of a liquid, and then we have it boils, and then we have a picture of gas. Or if you go this direction, the gas cools and condenses into a liquid, cools and freezes into a solid. So as the temperature increases this direction, heat increases this direction. So think about what's happening at each section. Here, the temperature is increasing. All right. Well, temperature, remember, is a measure of kinetic energy. So what's happening here is that the particles are collecting energy, and they start to move. And then eventually they break away from each other. But take a look here. This is a flat plateau. That means that the temperature is not changing. That means the motion is not changing. What's happening instead is that the particles are changing their arrangement. Here they are staying in the general arrangement, but they are wiggling away from each other faster, 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 faster as the temperature increases. Here they are breaking away their arrangement and they're starting to make an arrangement that looks more like this. Here, the particles, once again, they keep this kind of general arrangement, but they speed up, speed up, speed up, speed up. Here, they are changing their arrangement, spreading apart from each other, but they're staying at the same speed. So just notice that the particles are either changing their arrangement or changing their motion. Think of that as changing their how fast they're moving, but not at the same time. And then the same thing goes backwards if you're removing energy. So this is an interesting thing that not all people out in the world would be obvious to them. They think, oh, if you are boiling something, it's getting hotter and hotter and hotter. But when it's actually boiling, it is not changing its temperature. It's not getting hotter. It gets hotter until it starts boiling. But then during the actual boiling, it stays the same temperature. You could actually try this at home. And within experimental error, you will see that once it really starts boiling and boiling for a while, the temperature doesn't change. So there's your fun homework for tonight if you want to do it. So let's think about that. Put your thinking cap on. No matter what the boiling point is, the temperature of a boiling liquid never rises above its boiling point. Why not? Think about that. Pause the video and keep up with your ideas. All right, welcome back. So here's the idea, okay? So you have something that's boiling. Doesn't matter what's making it boil, doesn't matter the liquid. Boiling temperature is the temperature at which there's enough particles that have enough energy to break through the atmosphere pressure that's pushing down on it, and it actually turns from a liquid to a gas. So that's what boiling is. That's what boiling means. But the thing is that once boiling starts happening, think of it kind of like the evaporation. Where are the highest particle energy going? Particles with the highest energy, where are they going? They're leaving, right? So once they have enough energy to leave, then they are not measured in that liquid anymore, because that's where you're measuring it in terms of temperature. So those hottest energy particles, so all of these particles have about the same amount of energy, and the highest ones are leaving. So that means that they maintain the same amount of energy the whole time. You add more energy, the particles leave. So these particles left behind are at the same temperature. Once they have enough energy, they leave. So this whole thing stays the same temperature, and they keep collecting energy. So that's an important thing to realize, like I said, that not just general people out in the world, that wouldn't be obvious to them. So you got to think like a scientist here. And that's true for any phase change, not just boiling. While something is melting, while something is actively freezing, it doesn't change its temperature. Instead, it's changing the arrangement of the particles. So that's a big deal to think about in terms of boiling and phase changes. All right, I have this diagram for you. You don't necessarily need to draw it unless you want to, but I want to talk about that it's not just temperature that affects whether you are boiling or freezing or melting. For example, if you look at this, that you can have ice at a higher temperature if also you have high pressure. So that's what this is showing. Because think of it as like, I know you can't see me, but imagine that you have your hands out in front of you and bring your hands closer and closer and closer and closer. So imagine you putting pressure on objects, like particles. Well, if you put a lot of pressure on those particles can't move as much. Well, if they can't move around as much, that's our definition of solid particles. So high pressure, that force, can make particles almost sit still, and that would be like freezing. So, and then the other thing is just, I want you to be aware of this term. So there is a term called the triple point. So notice how you've got ice and water and water vapor that all connect right here. So this is when you have the perfect conditions that all three states of matter can actually be present at the same time. Okay, going into a level 2 kind of question about the stuff we've done so far. Maybe compare, contrast, maybe explain. That'd be a great one. Explain why the temperature doesn't change during a phase change. That'd be a great thing to review. Or explain how you could have cold water vapor, right? So that'd have to do with like if the pressure was really low, then even though the temperature was lower, you could have water vapor because those particles are free to move because there's not much pressure on it. So sorry, I gave you the answer to that one just because I realized we hadn't talked about that yet. Okay, you do your own level 2 question. Okay, let's finish this up by talking a little bit more about vaporization. So remember, vaporization is both evaporation and boiling. vaporizing just means that you're turning from a liquid to a solid. That's what I mean by vaporization. Usually, we think of vaporizing, so boiling, by adding energy, because that gives the particles enough energy that they break away from each other, liquid particles, and they turn into a gas. But we also need to talk about lowering the pressure above the liquid. And that has to do with something called vapor pressure. Anytime you have any liquid sample, there is always a little pressure right at the top of that liquid due to evaporation. There's always some particles that have been vaporizing, just a little bit. But normally, the atmospheric pressure keeps those particles that have vaporized right above the liquid. And so that's why we don't notice it. We don't notice bubbles. We don't notice the sample is like decreasing or anything, the liquid sample, because that vapor pressure is held down by the atmospheric pressure, which is the pressure surrounding anything. So, like the pressure around you right now is atmospheric pressure, but that's pushing on everything, solids, liquids, things around you, your body. So, atmospheric pressure is the pressure surrounding anything due to air. And normally that pressure pushes down on the liquid. So, those vapor particles right at the top of the liquid are kept in place. And then just a little bit about atmospheric pressure. Atmospheric pressure is often measured in millimeters of mercury or inches of mercury. Like if you hear a weather report and they talk about the barometric reading. So a barometer is what is used to measure atmospheric pressure. And this is an old-fashioned barometer, but that's where millimeters or inches of mercury comes from. There's like this inverted tube, kind of like a test tube, inverted into a dish of mercury. And if there's more air pressure, it pushes on the mercury. And then that means it goes up inside the tube. And then how many millimeters of mercury are in that tube would say how much pressure there is. So if there's more mercury up in the tube, then it's higher air pressure. So that's how a barometer works, even though, again, this is an old-fashioned one. Standard pressure, just to make a connection, is 1 atm. But remember, 1 atm is the same as 760 millimeters of mercury. Actually, that might be a new conversion that I hadn't given you before, but we have seen this one before, 101.3 kilopascals. We mentioned standard temperature and pressure when we talked about, do you remember? Can you recall? Molar volume. So just a little side note that generally what you are feeling where we live in Minnesota on a generally normal temperature day is around 1 atm or 101.3 kilopascals. So just to give you a feeling of, so like the pressure you feel when you're just sitting in your house right now is probably pretty close to 1 atm. A little bit lower in the winter, a little bit higher in the summer because of more or less energy particles in the air, the way they're moving, but that's about what you are feeling, just to give you a connection. Okay, now the last part of our notes I want to talk about is, what does it really mean to boil? I want you to come out of here with enough explanation of this. So what it really means to boil is that the particles gain enough kinetic energy, energy of motion, they're moving fast enough to break apart the attractions of other liquid particles. So liquid particle A to liquid particle B is kind of attracted. They roll over each other. If you give enough energy, those particles move fast enough and away from each other that they are no longer attracted. The particles turn into a gas, which is also known as a vapor, which means that if you have more particles turning into a gas, you'll have more vapor, which means you have more vapor pressure. Remember, vapor pressure is that pressure that's right above the top of a liquid, usually kept in place by the atmospheric pressure. All right, but if you have more vapor, you have more vapor pressure, which means it can break through the external or atmospheric pressure that has been pushing down on the liquid. Those gas particles now can break through that pushing, that force down, and they can escape the liquid sample, float out into the air. That's what boiling really means, right? So here's your vapor pressure. Here's your atmospheric pressure, the red dots. If you heat this up enough, these particles get enough energy that you get more and more and more and more vapor particles. So then if there's more vapor particles, that's what's showing you this like bigger arrow than this. More vapor pressure can push through the atmospheric pressure, and those particles can float out into the air, and that's when something boils. Okay, that brings me to a couple demos I want to show you. The first demo I'm going to show you involves a vacuum pump. And I'll talk a little bit about this in the demo, but a vacuum pump, just to make sure we know what it is, there is a motor that pulls all of the particles out from underneath this thing called a bell jar. If there's no particles, there can be no collisions between the particles. And if there's no collisions between particles, then remember there's no pressure. So Ideally, in a perfect situation, the motor pulls out all the particles so there's no pressure under the jar. So in the demo, you're going to see me because maybe you're thinking, okay, well, what if we put stuff inside that bell jar then, like a balloon? Or what if we put a beaker of water in there? Well, let me show you that. So enjoy these vacuum pump demos. Hello everyone, I got some demos I want to share with you today, and the first demo that we are going to be looking at deals with this thing called a vacuum pump. Let me kind of move my screen, you can see the whole thing. So this is what a vacuum pump looks like, and the idea behind a vacuum pump is that the motor pulls out all the particles that are underneath this bell jar so that inside there's no more particles. So that's what I'm going to just do first. So you'll hear it start to work when I plug it in. So you can see, so that motor starts to turn. And so right now, in a perfect situation, every air particle that is inside this bell jar is being pulled out. And that creates what we think of as a vacuum. So that means that now there's lots of particles out here. These particles barely changed. And then inside, there's no particles. Okay, so that's kind of an important thing. I'm going to unplug it. So we hear the motor turn off, but I haven't changed anything else about inside versus outside the jar. So the kind of interesting or weird or kind of cool thing that's happening is that this pressure is smashing down on top of this bell jar as hard as it possibly can. But the glass, it's really thick, so it doesn't crush it. But if this was thin glass, that would happen. So inside, there's nothing else balancing it. So no matter how hard I pull, and I'm not even just like being an amazing actress, like I am trying, like I'm pulling really hard, like I'm pulling on this and trying to get it off, and I can't because this pressure is so hard pushing on it. That was a weird sentence, but it's pushing on it so hard that I can't get this off. Okay, so either I have to throw away this vacuum pump or I have to figure out some way to get there to be pressure back in there so I can take this off and it balances it. Well, it turns out that all I need to do is unplug or release the vacuum. Listen to this. So what you're hearing is the vacuum releasing. So then now air went back into it. So there's air particles moving around in there, creating pressure pushing this way, balancing out the pressure pushing this way. And so then I can pretty easily take the cover off. So that's just what a vacuum pump is, and how, like, what vacuum means in the science world is that there's no particles, so there's no pressure, no kinetic energy of any kind. That's what's going on in a vacuum. So now what I want to do is I want to connect vacuum to pressure and then eventually boiling. So the first thing I'm going to put in the vacuum is a balloon. So just a balloon I blew up with my breath. So we've got a kind of a smallish balloon, and I'm going to put that in the vacuum pump. So I'm going to put that in there, and then I'm just going to let it kind of sit in there. And then I'm going to turn the vacuum pump on. I make sure it's still sealed. And so think for a little bit about what you think might happen to that balloon based on the pressure, what's going to happen to the pressure around the balloon. But then what about the pressure in the balloon? Let's see what happens. All right, check it out. So the vacuum is on. So all the particles around the balloon are being pumped out. But all the particles that were already in the balloon are still there. So those particles now are spreading out. So those particles are spreading away from each other, pushing on the balloon and filling up as much space because there's nothing holding that balloon to that original shape. So right now, like if there was enough space, but it looks like it kind of maxed out. So if there was enough space, that balloon would just keep going and going and going until it stretched the rubber of the balloon, and it would eventually pop because there'd be so much of the particles inside the balloon pushing out. But at some point, this just kind of gets contained. So even if I turn off the vacuum, so it stays that way. And then I'm going to release the vacuum. So let's think about what's going to happen to that balloon then. So again, right now, there's no pressure around the balloon, keeping the balloon the shape it was when it was outside of the vacuum. So then the particles inside the balloon could just keep pushing and moving and pushing and moving and expanding the balloon. The particles themselves aren't expanding, so we just be careful about our wording. But the particles are moving away from each other and spreading out more because there's nothing pushing it back in. So then I release the vacuum. So think about what's going to happen to the balloon. There you go. So it goes back to the original size because the particles in the balloon are still the same particles that were there before. Now the particles around the balloon are the same as the particles that are around the balloon out here. So then that's balanced. So now this pressure is keeping the balloon this size, And the pressure inside is keeping the balloon this size, so kind of between it. Because if there was nothing in the balloon, then this pressure would smash it really small. But because there's pressure inside the balloon, it's kind of like a balance. It doesn't get any bigger because of this pressure. It doesn't get any smaller because of the pressure inside. All right, so then seeing a connection between pressure and what's happening in there, less pressure, that kind of thing. Now let's connect it to phase change information. So what I have for you here is a beaker of water, and I know you couldn't see it before, but you'll just have to believe me that this is just a normal beaker of water. I didn't do anything tricky to it. There's no fancy tricks going on here, just regular water. And I'm going to show you the temperature. And so you can see that the temperature it's room temperature. So it's going down a little bit because the air was a little bit warmer than the liquid. So we see it's like 22.98. So it's going to be around there. It won't change much more than that. So remember that it's around 22.7. Seems like it's staying there pretty much. Okay, so remember that temperature. So 22.7 is kind of what it's settled on, which is about room temperature. So this is room temperature water. What I'm going to do for this demo, so let me reseal my vacuum. For this demo, I'm going to put the beaker of water in the vacuum pump. Okay, so there's my beaker. Get that covered in there. And then I'm going to make sure that you can see what's going on. And then I'm going to turn on our vacuum and we're going to watch it for a little while. Now this takes a little bit of time. So you might see the video skip a little bit, but there's nothing else changing during that time when I skip the video other than just like skipping ahead. I'm not adding or changing anything about what's going on in here. So watch this for a little while. There you go. Are you seeing it? So maybe you saw the little bubbles and now you're seeing kind of bigger bubbles happening. So just to clarify, there's no hot plate here. Nothing changed about what I was doing. It's just boiling because of that vacuum pump. So take a look at that. So we definitely making sure that I'm not convincing you, but you're hoping that you definitely can see that that is bubbling. It's not just the vibrations of the vacuum pump, but definitely there's boiling happening there. So making sure you agree with me, definitely it's boiling. All right, are we in agreement? Okay, now let me show you something. All right, so I'm gonna unplug this really quick, and then I'm gonna release the vacuum really quick so I can get the bell jar off. All right, quick. Okay, so it's obviously not boiling again right now, but remember, it was just boiling a few moments ago, like just a couple seconds ago, you saw it boiling. So let me put this in here. So just a little while ago it was boiling. Look at that temperature. It's actually lower than it was before. All right, so remember it was 22.7 and now it's like 21.6. It looks like it's kind of staying at. So it's actually a lower temperature than it was before. What? It was just boiling. How can it be colder than when I started this demo? This is one of those awesome mind moments when you're like, wait a second. So boiling isn't about adding temperature? Well, obviously it is. Let's think about what happened. When I have the beaker in under the bell jar, removed the pressure around it, I removed the pressure over the top of the beaker or around the beaker, right? Anytime you have some type of liquid, there is a little bit of vapor pressure above the liquid because the very top layer is evaporating. That's happening all the time at all temperatures. The very top layer of that liquid is evaporating. Normally, we don't notice it though because this atmospheric pressure keeps that vapor there. So there's atmospheric pressure and then there's vapor pressure right here and then there's liquid. And then there's also some air pockets inside between the molecules that molecules want to collect energy and they want to turn into gas, and that happens all the time anyway. But the vapor pressure that's right here is staying there and then we don't see anything happen. But remember what I just did. I removed that atmosphere pressure when I turned on the vacuum, which means that vapor pressure had nothing holding it down. So all those particles that were turning into vapor, they could now leave, which means then another layer could leave. And then that creates that bubbling. So that boiling that you were seeing had nothing to do with temperature changing. The temperature actually went down a little bit, but it still was a phase change between liquid and gas. And it's all about the vapor pressure. So the way you make something boil is that you allow the vapor pressure to overcome the atmospheric pressure. So how did I do that? I got rid of the atmospheric pressure. So then, of course, the vapor pressure is higher and can make something boil. So the purpose of this demo, one, I think it's fun, but also to make you think about that boiling is more than just getting something hot. Boiling is really, the science definition of boiling is really about have enough vapor pressure so that the vapor pressure overcomes the atmospheric pressure and can turn into a gas. Normally we do that because we use like a hot plate or something, or a stove or a microwave, and that gives the particles so much energy that they have enough pressure to push through the atmospheric pressure. That's usually what we think of as boiling, but that's not the only way. All right, so that's demo number one, learning some more about vacuum pump and pressure and vapor pressure. I'm now going to switch you over to demo number two. Enjoy. All right, so I hope you enjoyed those vacuum pump demos. I have another one I think you're really going to like. I'm going to do a demo where I boil with ice. What? That sounds like magic. How can you boil something with ice? It is not magic, it's science, I promise you. Enjoy this second boiling demo. Hello, and welcome to another demo about boiling. Okay, so first you can see, like, there's no big trick here. You're like, oh, Miss Kay, you are boiling something with a Bunsen burner. Oh, really interesting demo. Well, let's be clear. This hasn't started yet. This is just what we normally do for boiling. So let's review. If we want to make something boil, we are turning liquid into the gas phase. The liquid particles need to get enough energy to overcome the vapor pressure that is keeping everything liquid, overcome the vapor, or the vapor pressure overcomes the atmospheric pressure, and those particles are allowed to turn into a gas. So the way I'm making the boiling happen here is by adding heat. So the Bunsen burner is going, it's heating up the liquid. That's giving the particles so much energy that they create more and more and more vapor pressure. When there's enough vapor pressure, it pushes through this atmospheric pressure and it starts to boil. So that's what we normally think of as boiling, right? No tricks, normal kind of thing there. So what I'm going to do for this demo is, instead of boiling it with heat, I am going to boil it with ice. So what I have here is just some ice chunks that I've made in the bottom of like a styrofoam cup, so just that they're a little bit bigger. And what I'm going to do is I'm going to turn off the Bunsen burner. You can still see that it's very hot. You can see the steam. There's definitely gas in here. So there's definitely, gas that's happening. And then I'm going to put the stopper on this, okay? So I'm going to cap it. So now think about what I did. Now there's lots of really, really hot gas in this part, and then there's really, really hot liquid in this part. Okay, so then now I'm going to grab it, and then I'm actually going to flip it over because of what I want to do. I want you to be able to see this part. So the green liquid is just food coloring, just so it's easier to see the liquid, so it's not clear. I'm going to take my ice cube, and I'm just going to put it at the top of, which is now the top of the flask, and just let that sit on there for a little bit. So think about what I'm doing. So I'm putting ice on the top, and think about what that's doing to the glass, and think about what that's doing to the air particles, steam that is by the glass, and now look at what's happening to the liquid. Definitely we would call this boiling again. You saw that it had stopped. The liquid had all stopped moving. It had gone back to just liquid, but then now look, it is boiling again. You can see those bubbles rising. And just to be clear, there's no tricks here, right? No strings, no tricks attached. I'm just holding it on the bottom so that, and then resting it on the tabletop so that I can hold it a little bit better. But now we would call this boiling again. You can see the bubbles forming and they come to the top as I put the ice on the glass. All right, let's talk about what's happening. So boiling happens when there's enough vapor pressure to overcome the atmospheric pressure. Think about what I'm doing now. The ice is cooling the glass. So that means any of the steam, the water particles that had turned into gas, or air particles that are by the next to the glass, they are also slowing down. If they're slowing down, that means there's less pressure. So now there's less pressure above the liquid, which means there's less atmospheric pressure pushing down on the liquid. So the vapor pressure that had been building up there because the liquid was really hot, because remember, it just came from the Bunsen burner, that really hot liquid with so much vapor pressure, that vapor pressure is able to push through the decreased of atmospheric pressure that was above it. Let's see if we can get it to go one more time. So I'm able to boil the liquid. Yep, here it goes again. Once again, you saw that it had stopped. So no tricks here. Like, this is actual science, no magic. I'm not using sorcery, but I'm able to decrease the atmospheric pressure above the hot liquid. The hot liquid has a high vapor pressure because it's really warm. Those particles have lots of energy. So when I decrease the atmospheric pressure above the liquid, the particles that are wanting to cause vapor pressure have less competition. So then that vapor pressure can increase and then make it boil. So thanks for watching this demo where I boiled something with ice. See you next time. All right, it's time to put those demos into words. Think about what you just saw. Here's the 2 questions. I want you to pause the video and think about this for a little bit. Why does the water boil in the vacuum pump with no added energy from a heat source? And second question, why does the water start boiling again when ice is placed on top of the container? I mean, that sounds like madness, but it's not. It's awesome chemistry. So you pause the video and think about those 2 ideas, put some thoughts down. This is kind of a way to see if what we saw today makes sense. And then let's finish up with a level 3 question. So some type of prediction or argument, or you could think about something that happens in space, because generally we think of deep space as being a vacuum with no particles around. So you could think about that kind of thing would be cool. All right. All right, and then I'm also going to give you the answers. So take a look at these answers. You can pause the video if you need to. Make sure you put something like this. I talked about it in the demo videos, but I want to make sure you can put it into your own words. So pause the video if you need to read through these answers to these 2 questions. All right, so then that brings us to the end of the second day of this unit as we continue to explore more about states of matter and the chemistry related to that. So here's your to-do list. Go back and finish any CASTA questions if you did not already do them during the video notes, and then write your summary that answers today's essential question. There are some unit practice problems related to today's notes, and these would be a really good idea to work on because I don't have any other new assignment for you. So the way you'll really make sure you understood today's notes was maybe to look at some of these unit practice problems. You could either write them down, somewhere in the back of your notebook. But even if you just looked at the questions and thought about the answers or answered them out loud to yourself and checked the answers, that review and processing will help you understand this material or help you know whether or not you understood today's material. So I would highly recommend those. Remember, they're in the week 11 folder, not in a daily folder. And then the other another thing you could do that would sort of help you process some of today's information and other information from this unit was the Kinetic Molecular Theory supplemental reading. It was in our last class folder. So whichever day you had class, so today's day 2. So whatever day you had day 1 in class, it's in that Schoology folder. You can just put it into Notability. There's nothing specific you need to do with it, but spending some time reading through that will supplement some of today's notes and day 1 notes, and then also day 3 notes. So again, there's no new assignment today because I understand obviously that our notes were pretty substantial, but it might be good for the rest of our class time, which might be around 20 or 30 minutes. Not a new assignment, but maybe look at some of these unit practice problems, check the answers, look at this reading, just to kind of help you process the new information from today. All right. So if you watched this video on the day it was assigned, the next time I see you will be our last Zoom session. Otherwise, if you're watching this any other time, I just appreciate your attention and thank you for learning more about phase changes and the chemistry involved with that. See you next time.